Okay, welcome to 2.6b, and here today we are focusing on the inverse trigonometric functions and their derivatives. So first off, a little bit of introduction just about the inverse trig functions. So a quick review from your pre-calc class talking about the necessity to have a one-to-one function in order to make an inverse happen. So they have to be strictly monotonic. And in order to do that, we need to take like a sine function. Well, we know what a sine function looks like. Sine function, something like this. Well, this would definitely not pass the horizontal line test. So as is, the sine function does not have an inverse function. However, if we restrict its domains, we can turn this into a one-to-one function, and that's what you see happening here. So arc sine, if and only if sine of y equals x, I'm just reading the function stuff, the domain will be from -1 to 1, and I'll restrict the range from -π/2 to π/2. Because remember here, this was for sine, wasn't it? So this was our sine function. Well, the domain of sine, if I'm on -π/2 to π/2 for the domain of sine, then the inverses range will be the domain from the original function. So you're seeing here, I'm just kind of focusing on this right-hand column. There are some restrictions then of our range because we have to restrict the original functions to just certain regions to turn them into one-to-ones and create this inverse possibility. So you're looking at the inverse trig graphs, and then we'll do just a little bit. I think rather than doing every example, I'm just going to give you one or so from each little segment until I really want to get to the derivative part. So evaluate each of the following. Arc sine of -1/2. This question really is asking you, there is some theta. When I take the sine of theta, I get out an output of -1/2. Well, think about your unit circle, of course. -1/2 would happen down here at π/6, wouldn't it? Sine value would be. So the answer to this particular problem would be theta is π/6. All of these are looking for an angle measure. What angle gives you these values? Okay. If I did tangent of theta equals π/3, and if you recall, that was up here at π/3. So the theta value on this one would be π/3. Tangent is going to be restricted to quadrants 1 and 4 to get our answers out of the inverse function. And I can see, where's tan? Tan right here. Yeah, this describes quadrant 4 and 1. So that's a little bit about finding those first A through D, those first 4 there. Example 2, find the exact value of expressions involving inverse trigonometric functions. So I know that tangent of some angle is a TOA, opposite over hypotenuse. I could even think this number 3/4 represents opposite over hypotenuse. So I have some tan of theta equals 3/4. And that would be a triangle that has opposite over hypotenuse. Okay, so we got 3/4 hypotenuse. Now that will be with this angle theta. So I come down now and look at the sine of theta, because the answer to this is an angle, isn't it? And it's this particular angle right here. If I take the sine of this angle, sine is opposite. Oh, I put this in the wrong spot. That's what's going on. Oh goodness, you guys, I really screwed this up. But I was looking at sine out here. Opposite over adjacent. right, is tangent. And that will make 3 over 4 opposite side of my angle, adjacent side of my angle, and this will be the hypotenuse. And I could use Pythagorean theorem. 3, 4, 5 is what that triangle turns out to be. So sine of theta. Sine is opposite over hypotenuse, what I was referring to earlier. Opposite is 3, hypotenuse is 5. So the solution to this particular one is 3/5. For 3a, we're doing cosine of sine inverse. Once again, I'm going to have sine of some angle equals x over 1, and that's going to represent opposite and the hypotenuse side. So let's mark our theta angle and then put into place opposite side is x, hypotenuse is 1, and then doing the Pythagorean theorem, it would say hypotenuse squared minus a leg squared would equal my other leg squared. Let's do another leg squared. And then square root. So we can get down to just what that other side is. Oh, it's 1 minus x squared. Okay. So now I found the adjacent side as well. So I have my triangle completely filled in. The answer to this solution is some angle. And so now I do my outer function, cosine of theta, and cosine compares adjacent to hypotenuse, and I'll have root 1 minus x squared divided by the hypotenuse of 1. So it looks like the solution is simply square root 1 minus x squared. That should hopefully be somewhat familiar from last year. You just needed to get brushed up on it a bit. On the back side, this is where we pick up the calculus. You can see there are 6 different rules for the derivatives. The derivative of arc sine of u, where u is some function of x. I will do u prime, that's chain rule idea right there, over square root 1 minus u squared. Cosine is almost identical. Look at that, the similarities. Everything's the same except for the little negative. Arctan has no square root in it. It does embed the chain rule with us, so we get u prime over 1 plus u squared. Oh, look at the similarities here. Everything's the same except cotan picks up a negative. And here is your arc secant rule. It matches up with your arc cosecant, except for arc cosecant has a negative. Like we've talked before, anytime I take the derivative of a trig function that starts with c, I know I'm going to end up with a negative derivative. And that rule still holds true. So cosine, cosecant, cotangent, arc cosine, arc cotangent, and arc cosecant all will have negative derivatives. So how to do these? Well, let's first identify the u part. There's my u. And arc sine, which can also be written this way, arc sine of u, its pattern, I don't have mine showing because it's just up above here, is u prime over the square root of 1 minus u squared. These are the final derivatives that we have to learn, and then we've mastered them all. So you're on the final trail of this derivative trip. All right, so we know our u. We need a u prime and we need a u squared. I think sometimes it's handy just to make yourself a little list of those particular terms. So I want to square this. You can see I've been working away on this. My u identified as 2x. Its derivative was 2. If I square u, not squaring the derivative, but squaring the actual u, I get 4x squared. Now I just got to plop in place the particulars, right? So follow the pattern. The derivative of this function will turn out to be u prime is a 2, square root 1 minus, I need a u squared, my u squared is 4x squared, and that is done. Arctangent, we've got a 7, arctan 3x, this is my u, this is just a coefficient, a multiplier, so we can leave that hanging out there. I get dy dx equals 7 times whatever the pattern is for arctan. Arctan's pattern, look up above, you'll see it's u prime over 1 plus u squared. And we said our u, we can identify here as 3x. I'm going to need its derivative. So u prime is 3, and u squared is 9x squared. Take and plug it into this. So I get dy dx equals 7 times u prime, that's a 3, over 1 plus u squared. My u squared is 9x squared. Almost done, because this is so easy to simplify. It would be counted incorrect, or you would get points off if you didn't finish that problem by simplifying. Okay? 21 over 1 plus 9x squared. The next one looks a little bit more difficult, doesn't it? So our u in this case is x to the 1/2. Take its derivative. I have 1/2 x to the negative 1/2. Oh, that's right. This one has that nice little pattern where the square root drops to the bottom. So I get 1 over 2 square root x. And then u squared would be taking the square root of x, or x to the 1/2, and multiplying it by 2, or squaring it. And that's going to give me just x. Squaring a square root will produce x. The pattern for tan is u prime over 1 plus u squared. So my derivative dy dx is going to be u prime. U prime is this, 1 over 2 square root x divided by 1 plus u squared, which is x. Now, let's pull this together. This is a fraction, if you want to think of it. Multiply by the reciprocal of that. And our answer will look like 1 over 2 square root x, parenthesis 1 plus x. There's your derivative. For letter D, I see an outside squaring. This is a composite function, isn't it? I could think of my outer function, which we've often called f of x, just being something squared. I have a middle function on this one. I'll call that g of x. G of x would be the inverse secant function of x. And then my inner function, let's call it h of x, is e to the 2x. So we built up layers, outer, middle, inner. That means I had f of g of h of x. And to take its derivative, I take the derivative of the outer, leave the inside, multiply by the next layer, which is g prime. So I'll have g prime at h of x, and then I'll have h prime of x, right? Those 3 layers create the chain rule for us. So let's start with our outer squaring. Slide that over. The outer squaring, the way to take a derivative of something squared is to bring down the 2, change the power to a 1. And we have it at g of h of x, which is this stuff. So secant inverse of e to the 2x. Okay, got that layer done. Now I'm going to chain off. And my next thing, I said my middle function is a secant inverse. Secant inverse has a pattern that goes u prime over absolute value u square root u squared minus 1. Now, this u prime is really going to be the derivative of the e to the 2x. It has embedded in its little formula the chain rule already. So we're going to get these two actually accomplished in one step here. So my u is e to the 2x. My u prime is 2e to the 2x, chain rule. U squared is e to the 2x getting squared. Power raised to a power means I multiply my exponents, so I'd have e to the 4x. Notice it's not e to the 4x squared. It's just e to the 4x. Multiply these out. So into the pattern work. I'm following this pattern. U prime, here's my U prime. 2e to the 2x over absolute value of u, absolute value of e to the 2x, and then square root u squared, got it, e to the 4x minus 1. Okay, so that pattern worked out, and like I explained before, we did do the derivative of e to the 2x right here. So I have my 3 levels done of my composite function, and pretty certain I've got a good thing going here. I just need to simplify. So 2 times 2 makes 4. Secant inverse of e to the 2x times e to the 2x over. Are my absolute value signs absolutely necessary on this particular problem? Well, let's think about it a minute. If I have e raised to a positive, that's no problem, that's going to be positive. What about e raised to a negative? Well, raising it to a negative does not make it a negative value. It just makes it drop to the denominator. Notice that this still is a positive quantity, isn't it? And for that reason, this, even though I have a negative exponent, it will never be a negative number. It'll just get smaller. It'll be a 1 over e to that negative exponent. But it'll be 1 over, so it'll go to a positive exponent. So really, guys, we can eliminate these absolute values and allow this e to the 2x to cancel e to the 2x. And then we get our simplified form. Oh, so sorry. I just noticed I grabbed the wrong e to the 2x there. It's this e to the 2x going with this e to the 2x. Secant needs that 2 e to the 2x inside it. So this is gone as well as this. And there's our answer. All right, hopefully that's kind of enough that you can get a little bit better taste of inverse trig derivatives.